everyone, welcome back. In this lesson, we're going to look at simulating the sampling distribution of a mean. So we're lucky that the normal model can provide a good approximation for the sampling distribution of a sample proportion. But it might be useful to know the sampling distribution for any statistic that we can calculate, not just the sample proportion. So for example, the mean. Is the normal model a good model for all statistics? If you could take a second to review the purple box, and then we're actually going to look at a simulation. So let's simulate the sampling distribution of a mean. We're going to start with one fair six-sided die. We're going to toss it 10,000 times. And what I'd like you to do is predict what the histogram of the numbers on the face of the die will look like. Okay, we're going to go to this website. So if you just type in GeoGebra and then search for like GeoGebra dice simulation, this website will come up. We're going to use the slider to change the number of dice to 1 and then click on 10,000 to see the dice rolled 10,000. We're going to look at the histogram, and then we're going to keep doing that, but we're going to increase the number of dice to 2 and notice some things about the simulation. So again, if you just type in GeoGebra and then dice simulation, okay, and you're going to click on the first one. And we're going to change the dice. So use the slider where it says dice equal 2 and just click on it and slide it down to 1. And we're going to click on 10,000 to see the dice rolled. So before I do that, think about what the histogram should look like. And if you guessed a uniform distribution as the shape, you're correct, because it makes sense. When you're dealing with a die, the probability that that any one of the 6 faces will land up is 1/6. So it should be a uniform distribution, because all of the if you were to look at a large number of times of rolling die, the frequency of getting a 1 through a 6 should come close to the same. It should approach about 1/6. That's probability, which you can see here. If you take the probability of rolling a 1 here, a 1 appeared 1,695 times. If you divide 1,695 by 10,000, you'll get 0.1695, which is very close to 1/6, as well as are all of the other ones. Okay, so now if I change the slider to 2 and I roll the die 10,000 times, what do you notice happens? So now the shape is more normal, right? So there's 2 things that you should have noticed that are important. When I increased the sample size, the number of dice, as that gets larger, each sample average is more likely to be closer to the population mean. Okay, and we saw that if we go back to our simulation here. Okay, we said that the probability of obtaining any one of the faces on the die was 1/6, and we saw that in our distribution. Now, if I take die and I was to take 2 of them and roll them, right? That 7 there is representing the average of the sum of the dice. So 7 will appear the most. It has the most combinations, right? Because you can use a 1 and a 6, a 2 and a 5, a 3 and a 4, and then, the reverse of all those. So 4 and a 3, a 2 and a 1, and a 5 and a 1. A 2 and a 4, and a 5 and a 1. So it'll approach the true mean, and the shape is approaching normal, which is not a surprise. So in summary, the sampling distribution of any sample mean becomes more nearly normal as the sample size grows. Okay, this is true regardless of the shape of the population distribution. And this is a very important theorem. It's known as the central limit theorem. also known as the CLT for short, or the fundamental theorem of statistics. It's one of the most important theorems in statistics. Okay, let's check out an applet, a simulation, to see exactly what's going on here. So if you just type in like online stat book, and then you type in sampling distribution, this will come up. Or you can, type the link that's in the notes. And what I have here is a population, which you can see as normal, okay? I can change it to any type of distribution. So let's say uniform. What I'm gonna do is I'm gonna click on animate, and it's going to pull 5 random blocks from that uniform histogram. Okay, so if you click animate, there's the 5. And then what it did was it dropped that blue block there, which is the average of the 5 blocks. And it can do it again. Like if I click animate again, it's going to do the same thing. It's going to take 5 more random blocks and then put the average. Okay, and I can keep doing that. There's 5 more random blocks in the average. Notice that the blocks are clustering in a certain area, and off to the left, it keeps track of what the mean is. Now, if you look at the mean of the population at the top, it says it's 16. The standard deviation is 9.52. Okay, let's say I don't really have time to keep clicking 5 times. I mean, I could keep doing it if you, if you wanted to, but let's do it quicker. Let's click 10,000 and see what happens. So it's going to do the same thing we were just doing. It's going to take 5 blocks, find the average, plop it in that the histogram with the blue blocks. It's just going to do it 10,000 times. So click on it, and what happened? It approached normal because our sample size got larger. Also, take a look at the mean now. It says it's 16.06. That's the mean of the sampling distribution. And look at the mean of your population. It's 16. So it got very, very close, if not exact. Also notice the standard deviations. What happened? So as your sample size grew, right, it started out, the standard deviation was 9.52, and then the standard deviation of your sampling distribution for the means was 4.29. So it decreased. Okay, and that's really important. And you can do this for, any of the different shapes of distribution. So I encourage you to play around with it and see what's going on. And this really animates what the central limit theorem is all about. It just tells us that the sampling distribution of any mean or proportion is approximately normal, okay? But of course, there's some conditions that we need to check as well. So it requires essentially the same assumptions that we saw for modeling proportions. You've got to check the independence assumption and the sample size assumption. And then there's some related conditions. Since we can't directly check assumptions, we know we can check the randomization condition, the 10% condition, and then the large enough sample condition. There's no one size fits all rule, but if your distribution is roughly unimodal and symmetric, then your sample size is probably large enough. If it's shaped any other way, it may take many large samples to achieve a normal model. So the central limit theorem says that the sampling distribution of any mean or proportion is approximately normal. Okay, but which normal model? For proportions, the sample distribution is centered at the population proportion, P, as it was in the examples we did earlier. For means, it's centered at the population mean, which, if you'll recall, is mu. What about the standard deviation? So when it was the sampling distribution for proportions, it was the square root of P times Q over N. But we don't have P here, right? We have mu. So how do we find the standard deviation? It turns out that the normal model for the sampling distribution of the mean has a standard deviation equal to sigma, which is the standard deviation of the population, divided by the square root of the sample size, which is always n. So what's important to get from that is when random samples of size n are drawn from any population with a mean of mu and a standard deviation of sigma, The sample means, y bar, have a sampling distribution with the same mean, mu. So in other words, y bar and mu should be equal, as we saw in that applet, right? The mean was about 16 for the uniform distribution, which was our population, and then the sample, the mean was 16.06. So they were very close. And then the standard deviation is sigma over the square root of n. No matter what population the random sample comes from, the shape of the sampling distribution is approximately normal as long as the sample size is large enough. The larger the sample used, the more closely the normal model approximate the sampling distribution for the mean. I would take a second and read through that little clarification there, and then you can also read the example and unpause the video when you're ready to review with me. The Centers for Disease Control and Prevention reports that the mean weight of adult men in the United States is 190 pounds, with a standard deviation of 59 pounds. An elevator in our building has a weight limit of 10 persons, or 2,500 pounds. So, in other words, you could look at that as, the average weight per person would just be 250 pounds. What's the probability that if 10 men get on the elevator, they will overload its weight limit? Okay, so in other words, we're asking if the probability of the mean weight is going to be greater than 250 pounds. So we need to make sure we check our conditions, and the conditions we're checking again are independence, right? The weights of men are independent of each other. They should be, unless maybe they come from the same family or there's some similar characteristic. Is it a random sample? So it does say in there, it doesn't really say random, but the men getting on the elevator could be representative of all men, and it's safe to assume that. The 10 men are obviously less than 10% of all elevator riders. And if I was to graph weights, you can assume that they're going to come out to be approximately unimodal and symmetric, right? There's always going to be an average weight in the group, and then some a little bit more, some a little bit less. So that means it's safe to use the normal model here for approximation. Okay, so a couple things. They tell us that the mean weight of the adult men in the US is 190, so that's got to be my population mean, that's 190. And they tell me the standard deviation of the population is 59 pounds. So there's sigma, okay? So I need to find the standard deviation of y bar, which is my sample mean. And to do that, remember it's sigma over the square root of n. So it's just going to be 59 over the square root of 10. And that comes out to be 18.66. So if I was to draw my normal model, we know that the mean is in the center. And if I go 3 standard deviations in either direction, I'm just going to add 18.66 each time. So the next thing I want to find is z, my z-score. Remember, that's your value. So your sample mean, which in this case is 250, minus the population mean, which is 190. And then I'm going to divide by the standard deviation of the sampling distribution, which is 18.66. And when I do that, I end up with 3.21. So that tells me that my sample statistic, which is 250, is 3.21 standard deviations above the mean. And I'm looking for the probability that it will be overloaded. So that means that I would be looking to the right, okay, because that's where more weight would be. So I'm trying to find the probability that z is going to be greater than 3.21. And I'm going to use normal CDF for this. My lower bound is 3.21. My upper bound is 100. And your mean is 0. Your standard deviation is 1. And we end up with 0.0007. So what does that mean? It means that the chance that the weights of a random collection of 10 men, that's any 10 men, will average more than 250 pounds is only 0.0007. So it's a 0.07% chance that that will happen. So that means it's extremely unlikely that 10 people will exceed the limit. Okay, so we'll write that out here. Please be careful. Don't mistakenly think that the central limit theorem says that the data are normally distributed as long as the sample is large enough. In fact, as samples get larger, we expect the distribution of the data to look more and more like the population from which the data are drawn. Skewed, bimodal, whatever, but not necessarily normal. The central limit theorem doesn't talk about the distribution of the data from the sample, but rather about the sample means and sample proportions of many different random samples drawn from the same population. Here are some problems to think about. Human gestation times have a mean of about 266 days with a standard deviation of about 10 days. If we record the times of a sample of 100 gestations, do we know that a histogram of the times will be well modeled by a normal model? So we don't really know. No. So the answer is no. This is a histogram of individuals. It may or may not be approximately normal. We can't tell from the information that is provided, right? And we would also need to check our conditions. Suppose we look at the average gestation times for a sample of 100 women. If we imagine all the possible random samples of 100 women we could take and looked at the histogram of all the sample means, what shape would it have? So for this, we know it's a normal model. We know that because of the central limit theorem. Okay, and when we say a normal model, of course, it's going to be approximate because we're dealing with real life data. But again, the central limit theorem, or CLT, or fundamental theorem of statistics, tells us this. Where would the center of that histogram be? So it's going to be wherever the population mean is, which in the original problem it says that the gestation times have a mean of 266 days. So that's where the center of the histogram would be. What would be the standard deviation of that histogram? So remember, I'm going to take 266, I'm going to take the standard deviation, which is 10, and I'm going to divide by the square root of the sample size, which is 100, so you get 1. So the standard deviation is 1 day. Something to remember as we wrap up here is the two basic truths about sampling distributions are: sampling distributions arise because samples vary, and each random sample will contain different cases, and so a different value of the statistic. And although we can always simulate a sample distribution, the central limit theorem saves us the trouble for means and proportions. And before you go, you can take a look at the figure there. And of course, if you have any questions, please reach out to me. I'm happy to help, and I hope you enjoy the rest of your day.